Okay. So you can tell if the recording stops because the fan will stop. Network has been a little glitchy tonight, but hopefully it'll be good. All right. So tonight is a different sort of lecture. And it does, I'll admit, start out a little slow. Hopefully you can hear me. I just saw the link go down for a second, but I'm going to just keep going because it's recording. So starts out a little slow, a little obtuse to the topics we talked to, but it's going to come into something very useful. So bear with me at first. We talked about some basic kinds of stuff that might not be exactly related, but it proves a point. So let's get on with it. All right. So. Ugh. I'm watching the pinwheel spin here. So we're going to start out with time-based measurements. So we start out by talking about an oscilloscope. I can't get the slide to flip. I'm sorry. Can you guys hear me? See if that works at least. Okay. All right. Let's just give this a minute and hopefully things clear up. The computer's plenty fast. It's just the connection is slowing things down. Okay. Yeah. All right. So just give me 1 second. Oh, there we go. All right. So what's an oscilloscope, right? So is this circuit theory 101? Well, not really, but I wanted to find some terms. So of course it flips too. A time-based measurement. So a time-based measurement is a case where we have a time-based generator, something that's going to sweep in time, and then we're going to synchronize the data that comes in to that time. And what it's going to do is give us a snapshot of a given piece of time. And that's exactly what oscilloscopes do. And if you're an EE, you've used an oscilloscope many times. And if you're not, you probably at least know what one is. So that's the start of things, is a time-based measurement of a time-varying signal. Okay, so that's what an oscilloscope does. Now, the oscilloscope is what we would call a continuous measurement. And it's not really continuous, but it's continuous enough in that it takes measurements over a continuous range, not digital. Now, it gets digitized, and when it digitizes, it quantizes it, it puts it into steps. But potentially, there's so many steps that you can't tell. As a human, it looks like a continuous wave. So we call this a scope. We're going to call the type of thing that we're using a digital storage scope, because it's taking in samples of the analog data. So it stores the samples. And what we're going to do is have a buffer of these samples. So, we call it a scope. We call it a O-scope, some people call it. And we might even call it a mixed signal oscilloscope, but we're not going to talk about that for at least a half an hour tonight. And in the old days, that was a cathode ray tube. I have one downstairs, the old-fashioned cathode ray oscilloscope. So I was going to bring it up here to show you, but it's way too heavy to carry, so I left it down there. Okay, so it starts with probing, and this is where it gets important. And I know it's single probing, but a probe is a device that I can use to make a connection to a signal of interest. So the thing that I'm going to display on the scope, I'm going to connect a probe to. And you can see in that picture, the probe is connecting to a pin of an IC, and it's a gigantic pin. And I don't know what that IC is, but I'm guessing it might be about 100 gates, right? So back when ICs had about 100 gates in it, the connection was fine if you had to make single connections to it, which is another kind of piece of how we're progressing tonight. Okay, and the passive probes are 10-to-1 probes because it divides it by 10 and then amplifies it in the scope. So you get a truer signal. And I don't want to get too deep into that, but just to suffice it to say that you have a 9-to-1 ratio on a high impedance, right? So there's the 9 ohm and 1 ohm, so it's a 10-to-1 probe. And the importance of that is not necessary, other than the fact that it's going to reduce the noise. And the whole idea of the making a measurement is to measure as much of the signal as possible and as little of the noise as possible. And anytime you amplify something, you amplify the signal and you amplify the noise. So with the 10-to-1 probe, you have a 10-to-1 ratio on that. So it's passive. There's no amplifier in here. And again, that for our purposes, it doesn't really matter, but it does reduce the maximum frequency of the measurement, which is another problem here. So we're worried about noise, and we're worried about how fast of a signal we can measure. Remember that this probe, the cable on the probe is probably 1 meter long, and a meter is in the range of 5 nanoseconds. So there's that much delay in the signal just to get to the instrument. So lots of problems making these connections. So we can get a cheap probe, right, which doesn't have that compensation, and it is literally just cheaper. And again, the more we have, the more economical we have to be. Not that money necessarily has to be an object, but when we start to get into very large numbers, the density causes us to have some simplicity. So if you're wondering, where is this guy going? I'm going towards a logic analyzer, right? Something that has lots and lots of connections. So I'm stepping through to that point. I realize I forgot. 201A is 7004. Okay, the attendance code for 201A is 7004. The attendance code for 201B is 0571. So once again, 7004 for the in-class section and 0571 for the virtual section. Okay, so there's the low frequency probe. And then what does this do? My red circles shifted, or the picture shifted, but I'll point it out. So here's the display of an oscilloscope, and there's 2 settings here. One setting is the resolution for the channel. We only have one channel showing. It only shows one channel of resolution. It says 1 volt. That means each one of these divisions is 1 volt. So here's the thing. We don't care about this tonight because we're not measuring volts. We're measuring ones and zeros. So our measurements are not going to use a large number of bits. Sorry, I heard a I'll look in a second. Somebody sent a text. There it is. Oh, sure. One more time with the codes. 201A is 7004. 201B is 0571. Okay. The other axis, the horizontal axis, is time. Now, time is very important to us. And here we're getting a illusion that the time is continuous, that I can measure between any of these 2 points. But you can see there's some staircase pattern, some quantization of the signal. So it's still sampled, but it's sampled at such a high rate that at 1 microsecond per division, right, this distance is 1 microsecond, that it's a lot of samples. I don't know or care how many samples it is right now. If I was really looking to find out what the accuracy of a scope was for a specific measurement, then I would look that up. But for now, just know that I have a time base that's sampling this signal, and then a vertical measurement that I'm making that converts a continuous signal coming in to a sample, right? An 8-bit sample, 12-bit sample, whatever the resolution, the vertical resolution of the scope is. Okay. Our vertical resolution in logic is 1 bit. It's above a threshold or below a threshold, and that corresponds to a 1 and a 0 respectively. Okay, so we can visualize this. Scopes have the ability to put up cursors, and they'll make measurements too in a minute. So the peak-to-peak voltage, the period is interesting. When we talk about logic analysis, we're not necessarily talking about a period, but we're talking about how much time between two events. So these measurements are going to carry forward. Also, what I haven't talked about is triggering. What makes the signal start at a certain position? And it's this indicator right here. So this says, I'm sorry, I'm pointing wrong place. This indicator right here, which says when the signal crosses this line, I'm going to display the signal. And you can see that it crosses the line right there. So the trigger level is right here, which is about 1 volt above ground. And the trigger position is right in the center. So what does that mean? That's important here. And it's going to be important when we talk about logic analysis as well. So that says I have an event that I'm looking for. And that event in this case is the rising edge of the signal crossing the trigger point, which is 1 volt above ground. And that's going to allow me to display this signal. But the other thing that's going on here is the fact that I've been storing all of these signals in a circular buffer. So it says start displaying here, but it's also going to display everything it had in the buffer that led up to that point. So when we do logic analysis, and you know, in simulation, there's ultimate controllability and observability, but in logic analysis, we generally don't want to see what comes after an event. We want to see what led up to the event. So this circular buffer and the capability of setting a trigger, and the trigger might not be a voltage. In fact, it won't be a voltage in digital analysis. It'll at least be a sequence. So a pattern, I should say, on a number of logic signals. I don't want to get too deep in that because we will get to that in some slides. So there's cursors, right? And you can automatically put the cursors down, and the cursors will tell you the peak-to-peak voltage, and you can move the cursors up and down, and it will tell you the distance between them. There's an A cursor and a B cursor, and so it'll give you the ability to make vertical measurements, but most importantly, it gives you the ability to make horizontal measurements. And the vertical measurements are in seconds, in this case microseconds, and the I said that wrong. Horizontal measurements are in seconds, and vertical measurements are in volts, right? So you can figure this out and look at it and see that it basically means. And then delta X. Delta X is the distance between these two cursors, which, you know, you look carefully, that's half a wave of this sine wave, right? So this continuously changing signal, half of that is 2.52 microseconds, and that's going to translate to about 400 kilohertz, right? So that would mean the signal is about 200 kilohertz because this is only half the wave. So the measurements become very valuable, especially when we have a lot of signals. So we have a reference point and then a point that we're measuring relative to that too. The voltage measurements, again, are going to come out just as a sequence, a pattern of ones and zeros on a logic analyzer. So it will make measurements for you. So notice there's no cursors here, but we got a whole bunch of measurements. And depending on the capability of your scope, it gives you a wide range of measurements. I have about $100 USB scope here. It doesn't have very high bandwidth, and it has all these measurements on it. It's only like 20 megahertz bandwidth, but it plugs in USB. I probe the things I want to probe, and it comes out on the screen of the laptop. Okay, so there it is, right? A whole bunch of things here. See, the frequency is 200 kilohertz, which I estimated from the previous slide. These tend to be a little more accurate than positioning the cursors because you're kind of arbitrary when you put positioning the cursors. But when they make measurements like the frequency measurement, it's nowhere near as accurate as, say, a spectrum analyzer, which is a frequency measuring tool. An oscilloscope is a time measuring tool. So this is what the outside of the box looks like. You've seen these in labs. You've seen them all over the place. You might have read, might have used them yourself. This is a a fairly simple device. It has 2 channels, so you can display the yellow and the green. We've only been looking at 1 channel, so there's the yellow channel, the green channel, a couple connectors that allow you to connect the probes, an adjustment for the vertical size of the division, so the vertical range here. You adjust this and it goes 1 volt, 2 volts, 5 volts per division. You turn it the other way, it goes 1 volt, 0.5 volts, 0.2 volts, right? Turn it up and down. And then if you want to move the signals up and down, which is usual, just display-wise, which is useful when you have more than one signal. I find this a little confusing here when you have 2 signals on top of each other. So you can move one up, move the other one down with these position knobs here. On the trigger level, remember that was the point that we displayed the signal when it crossed that point. So that's there. There's other menus, and again, I'm not going to go through everything, but things to set specific events in the trigger, things about the display, even like changing colors and things like that, and then picking specific measurements. Okay, the last useful thing is up here, and it's the horizontal scaling. So that's the resolution of the horizontal axis here. So we saw that it was 1 microsecond. You turn it to the left, the number gets bigger. You turn it to the right, the number gets smaller, right? Because the resolution goes up when it's a smaller value, meaning the time base is going faster. And then we have the run button. So the run button waits for a trigger, and it will trigger every time. And you can click single, and it will only trigger once. So this is the 2 to 3 minute description of an oscilloscope. And really what I want to get across is the horizontal and vertical axis, where the horizontal axis is measuring the voltage and it's quantizing it into a digital number. Our digital number for actual digital signals is a 1 or a 0. It's a single bit because we're looking at it to be above or below a threshold. An oscilloscope is a quantized analog signal. So it might have 256 or 4096, some number of steps based on the number of bits. So if it has 8 bits, it's 2 to the 8th steps. So this is hard to read. This is not hard to read, right? So you want to get it scaled so you can see about a wave or two, and you see full scale so you get as much resolution as possible, right? You don't want to jam it all into one place. And that's what these knobs do. So this is just a slide describing what I was talking about. I had it all set up right, or actually the place that I got this stuff from. It's from a Hewlett-Packard Agilent Keysight, whatever the company name is now, kind of app note that they had on how to use it. So it was all good pictures and good description. So I just used it, and you can find it in the bottom of the slide there. So, give yourself as much room as possible, right? That's what it comes down to. And I'm just going to step back one. This scope doesn't have it, but a lot of scopes, oh yeah, it does right there, auto scale. So if you're measuring something like this and you press auto scale, it's going to end up giving you a signal like this. So depends, right? I usually hit auto scale. It gets a signal about what I want and then make adjustments to get exactly what I want to see on the screen. Sometimes you want to see a lot of detail in here, and it's a sine wave. So you blow it way up and the signal, that rising edge sweeps across the whole screen, but you get a good view of what's going on it, especially with digital signals that have bounce in them, right? So you can see that bounce in the slope. So this is what it does, right? The triggering of the scope. So they use the photo finish for the horse, which is a good example, but not perfect. So the idea here is there's some sort of optical trip here. And when something disrupts that optical signal, it takes a picture, right? And it takes a picture showing a lot of what's going to happen and some of what already happened. So if for some reason we had a smart optical sensor that looked at the second horse coming through, so this horse had proceeded through, we'd see that, right? We'd see the second horse through, and then the trigger would be on the second horse, right? So we'd basically be moving this line backwards. So as I said, it's usually more interesting to see things that lead up to the trigger as opposed to things that happen after the trigger. So this is kind of opposite, but it's a good idea of what triggering is. Okay. The picture isn't a picture like this. It's the buffer that was the buffered waveform that gets played out from the circular buffer. If it's not triggered, the signal just keeps writing over itself in some random position. If it is triggered, and here's the trigger point right here, when it crosses that trigger point, we get a signal. Now you might think, why didn't it happen here? Well, because it happened here. I'm not trying to be facetious there, but this happening over and over and over and over. This is a continuous wave signal. If I raise the trigger point and say I want it to look for the falling edge of the signal, then it's going to look like this. But this isn't really one wave of the signal unless I hit single. It's just a continuous picture. So if I have an unstable signal, something that's, say, being amplitude modulated, I'd see that variation in the signal here. I'd see it jumping up and down, but this trigger point wouldn't change because that's the point where I'm taking the picture. So it's always going to give me the picture of the point that I selected. But if this frequency modulation, that wave would be going, in and out. If it was amplitude modulation, I'd see it go up and down. But all the time, as long as I was crossing this point, the trigger point would be right there. So usually you do something more like this, where the trigger point is in the middle of the signal, and that way it doesn't jump up and down. If it's amplitude modulated, you just see the motion up here and down here. But it depends on what you're doing, and the voltage isn't important to us tonight. The time is, and that's what we're trying to get to. Okay, so this is what's inside. I have some interface to the probe, right? The probe is coming in. The DC offset allows me to move the wave up and down. I amplify the signal. I said that before. And this is the triggering, so I'm not going to look at this yet. But then I have the analog to digital converter. In this example, it's 8 bits. So it comes out with an 8-bit value that's a quantized value of the incoming signal. The signal has to be within a voltage range, right? If it's outside of the voltage range, I'm going to clip it. I'm going to be at the highest value and the lowest value, and the signal will look clipped, right? It'll look flat top. And then it goes into the acquisition memory. The acquisition memory is a circular buffer that keeps a continuous history of what's going on in the signal. And then let's go down the bottom here. I have my trigger, and the trigger is based on a trigger level. This is a comparator. So when it goes either above, rising up through the trigger, or falling down through the trigger, it's going to trip this comparator. And depending on if I want a rising edge or a falling edge, it looks at the positive output of the comparator or the negative output of the comparator, which clips the trigger. Depending on the position of the trigger, it reads out this memory into the display. Right? So I have this continuous window, this history of the signal, and I read out the position of it relative to how I set up the trigger, right? The trigger at the end, at the beginning, and the middle, right? We saw some examples of that here. And triggering is going to be important. And when we do large digital analysis, we're going to really want to do complicated things with the trigger. And again, that's kind of the point that I'll get to tonight. All right. So bandwidth is important with everything. It's important with the logic analyzer, and bandwidth is affected by a lot of things. And one thing that bandwidth is especially affected by is the front end of the oscilloscope, right? That I'm going to click back on, this attenuator and the DC offset and the probe. So when you see an oscilloscope being rated at a given bandwidth, so I said earlier I had a 20 megahertz oscilloscope. That means at 20 megahertz, the attenuation of the signal from the point of the probe to my display is 3 dB. So you circuit theorists out there know that that's half. So my signal is attenuated by half at that point. So you don't use a 20 megahertz scope to measure a 20 megahertz signal. You need some headroom. So you probably, sometimes the people who sell scopes say it's a 5x difference. So if you have a 20 megahertz scope, the maximum value that you can rely on is 4 megahertz. Of course, they're going to tell you a large number. 2 or 3 is probably good enough, meaning 2 or 3 times the bandwidth. So if you have a 10 megahertz signal, you need a 20 or 30 megahertz scope. I'm only telling you this because the logic analyzer, the way I'm going to set up, takes out a lot of these bandwidth limitations. So it's good news. All right, so if you have a square wave signal coming in, and that's 100 megahertz square wave, you get on a 500 megahertz scope, you get something that looks about like a square wave. If it goes to the 100 megahertz scope, it only shows you the 100 megahertz fundamental of the square wave. So a square wave is the fundamental, right? It's a 100 megahertz square wave. So a square wave is 100 megahertz plus 300 megahertz plus 500 megahertz, right, for your analysis. And it goes down, right? So it's 100 megahertz plus 1/3, 300 megahertz plus 1/5, 500 megahertz, right? So the signals go down, but if you have a 100 megahertz scope, the 300 megahertz and the 500 megahertz don't make it through. So that's why this 100 megahertz square wave on a 100 megahertz bandwidth scope looks like this. Here it looks like this. We want the bandwidth to be able to give us a true digital signal. Now, if we were doing a sampling of this, a digital sampling of the signal, which basically we set a threshold in the middle, and if it was above or below, we would have a 1 or a 0 respectively. We would read something like this, but we're going to see a lot of jitter, a lot of noise, because the transition point is not as sharp as it is here. We're going to solve this problem. So there it is, required bandwidth for digital applications, 5x the highest digital clock rate, or 3x for analog applications. It's kind of what I said. I said 2 or 3, but close enough. Okay, so what else is there? So the sample rate, you're going to look at the sample rate when you're buying a scope. You're going to look at the memory depth. So how big is that circular buffer? And again, that's going to be really important to us in logic analysis too, right? How much can we store before and display after the trigger point? How many channels, right? Oscilloscopes are usually 2 or 4 channels. But if we have a logic analyzer, it's very likely that the logic analyzer has between 8 and 32 channels, right? Or more. But remember how hard I was making it out to be to get those 2 probes on 2 adjacent pins of a big IC. What's going to happen when we have to connect 32 of those? It very quickly becomes prohibitive. And they have, I have a logic analyzer, an old-fashioned logic analyzer downstairs, but it has 128 probes on it. And I can't imagine having 128 of those tiny little clip leads and having them all connected at any given time, right? There's always going to be some force that causes one to get pulled off or not make a good connection or touch the one next to it or something like that. So it's hard, and we're going to solve that problem. So how often can we update the waveform, what the display looks like? You can get a really good oscilloscope with no display these days. It just connects to USB. And then triggering modes. Now, I've been implying that the trigger is rising edge or falling edge, but there's lots of other things you can do with triggering. And for the oscilloscope, I don't care. I'm going to give you some information about that for logic analysis. But just know that the scopes and the logic analyzers come with some advanced triggering methods. All right. So there's the probe again, some more math that we don't care about because we're not going to use probes. Right? Probes are going to be bandwidth limiting. They're going to be mechanically difficult. And they're going to limit how many connections we can make. And so these reinforce that when I talk about these things. You have to compensate probes, which again, if you're using probes, you have to connect it to a reference output on the oscilloscope, and you muck around with a little screw on the side of the probe, and it makes the improperly compensated probe that looks like this a properly compensated probe. right? Makes sense, right? Remember what I said before about if this edge isn't nice and sharp, you don't get a good trigger on that. You want that to happen basically between 2 or 3 samples, the transition that is. The more load you put on a probe, the less response, because remember, if you have a resistor and a capacitor, so if you have a impedance, a reactive load, it's going to reduce your bandwidth. So everything, connections, cable length, the connection onto the front of the scope and the front end of the scope all affect the bandwidth of the signal. So what you end up doing is having to spend more money and having a more complicated connection and scope. Read money, 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 right? You can get a better scope, you just spend more money. All right, so now the transition into logic analysis. So on a scope, we're looking for a voltage and we're looking for the continuous transition of that signal. On a logic analyzer, we're looking at the discrete change in the signal. So on a oscilloscope, we're looking at something that has many samples over a range. So it's an 8-bit A to D converter. So, reasonably, if we're not too close to the top and bottom, we can get 200 samples from the lowest to the highest of a transition signal. But that's not what we want to see. We just want to know when it's low and when it's high. But we want to see a lot of them. So that's what a logic analyzer does. So we see many signals, but we don't get the detailed resolution of the signal, but we make that concession because we know that it's very likely there is not much resolution to see, especially inside the chip. Right? We're not going to have, we shouldn't have analog type of problems on signals inside the chip. I'm specifically talking about FPGAs here. ASICs you can, but usually when you have problems on an ASIC, that linear problems on an ASIC, it's on the pins. Okay, but what we want is a very flexible triggering method. We don't want a low to high on a single signal. We want to be able to set up complicated triggers. So let's picture going back into simulation. When you're in simulation, you put in a bunch of stimulus, and then you look at the response, and you have this large number of signals over a long time. And then you go looking for an event. And when you look for that event, you might be looking for a pattern. So if you have a bus and you want to see when the bus is, say, CF, well, you go through, and probably with a search tool in the waveform viewer, it'll show you when that bus is equal to CF. And when it's equal to CF, you can see the value of the other signals. So you've observed, and I won't say trigger because triggering is a real-time thing, but you've observed a given signal at a given time. Right? You observe that value. And then from there, maybe use the search to get there, but from there you can look at the signals around it. You have the luxury in simulation of having the data all presented to you. In a working system, it's continuously running. So you need that trigger to say, hey, when FC comes on that bus, do this, right? Show me everything that happened before it and happened after it that will fit in the buffer. Maybe you want to bias it towards the end. Maybe you want to bias it towards the beginning. That's based on what you're doing. And sometimes it's also a sequence of events. So let's trudge on here. So what we're doing is we have this signal, which may or may not be a sharp digital signal, and we're sampling it based on it being above or below a threshold, and we get a sequence of ones and zeros. Now, be careful if you're buying a logic analyzer. That I should have taken it up, but that USB scope that I have also has a 16-bit analyzer in it, but it has what I consider an oscilloscope time base. I'll explain that a little later. So now if I have something that's more digital, I sample it over and over, right, at these positions. And if this is 36 nanoseconds here, this is about 3.6 nanoseconds per sample. right? He says 4 nanoseconds, doesn't quite fit, but you get the idea, okay? So in 4096 4 nanosecond samples, we get this sequence, and you can add it up, right? It's 16 microseconds. That's 50 microseconds there. So there's the event, a long time, and the event. So what we can do is tell the logic analyzer to not only trigger on things, but to sample on things. So what it would do is take a lot of samples during the time when there was something interesting and virtually no samples in the meantime. But it would time that event. So when it showed me the display, there'd be a space in the display where all the signals were the same, and then a place where it wasn't. So what that does gives me a more time to look at with the same size buffer. Now, if you go out and buy a $50,000 Keysight logic analyzer, it has tons of memory in it, and honestly, you should never. You're just not tracing things right if you're filling that memory, not seeing what you're getting. But the way we're going to do logic analysis, we have to be economical about the memory that we use. All right, so that's that. He shows a lot of granularity here, but I just noticed that my weather isn't updating. It says it's 47F, it's more like 47C. Anyway, no, that'd be too hot. All right, so triggering now. We want to, in our case, do pattern triggering. We didn't have the ability to really do pattern triggering on the oscilloscope that had 2 probes. Some 4-channel oscilloscopes will give you a very rudimentary pattern triggering, but that's not what we want. And then also edge triggering, which I already explained. So with pattern triggering, now I have something that's much more likely to be a digital signal. We want to see, for example, when we have a memory request that's a read versus a memory request that's a write. So it's a simple pattern, but it's a 1 and a 0 for a write, and it's a 0 and a 0. I'm sorry, I said that wrong. 0, 0, 1 is a read, right? Because write has to be high, and then 0, 0, 0 is a write, right? Because I'm looking at the pattern of these 3 signals. Now, remember, back when I was talking about the oscilloscope, and on the oscilloscope, the sampling was asynchronous, meaning it was just sampling, right? And it was giving me a picture that it saw every sample. And if I did that here, I'd take a lot of samples and I'd get a picture. I'd have something that looked approximately like this. But I would use up a lot of samples because I have to at least sample twice as fast as these signals are changing. So I have to at least sample twice as fast as this clock, which means I'm wasting a lot of samples. And the sampling rate isn't continuously variable, so I probably more like at least 3 times the clock rate. Now, what logic analyzers have, and this is the difference between a scope time base and a logic analyzer time base, is on a logic analyzer, I can use an external clock as my time base. So that means I only have to take 1 sample per clock cycle, or maybe 2. Some allow me to have a rising edge and a falling edge sampling clock, but suffice it to say that it's both more accurate and more efficient in memory. So back to my $80 or so USB oscilloscope, it has 16 channels of logic analysis, but I found out after I bought it, not that $80 was a lot, but I found out after I bought it that the logic analyzer doesn't have an external clock input, which means it has an oscilloscope database for the logic analyzer. With that said, it has a lot of memory in it. So I can asynchronously sample and I don't have to worry about being efficient about the memory. And honestly, I use it for Raspberry Pi and Arduino projects where I'm looking at SPI buses and things like that. So it's not critical that I have a lot of memory. And it's only 16 channels, right? These larger logic analyzers have potentially hundreds of channels, and that uses up memory as well. But it's only 1 bit per sample as opposed to the oscilloscope. Okay. So an asynchronous clock is what I've been calling an oscilloscope time base. And a synchronous clock runs from an external clock, right, the system clock rate. And it is both an efficient use of sample memory, and it's more accurate because it's exactly one sample per period of the signal, as opposed to 2 or 3, right? If I had an asynchronous clock, or I could turn the asynchronous clock way up so it was 100 times faster, and I take a lot of samples, and I would get an accurate result, but my memory would fill up very fast because I'm filling up 100 sample locations per cycle of my system. So in logic analysis, you want to bias yourself towards an asynchronous clock. I only use asynchronous clocks in oscilloscope measurements, but I try to always use a space synchronous clock when I'm doing logic analysis. All right, we're only doing logic analysis, sorry, in the FPGA anyway. So very simple, right? You remember the oscilloscope picture. This one's much simpler because the input goes to a comparator. I set the value of the comparator to be the transition value of my digital signal, so I want it kind of in the middle. There's a lot of different digital technologies around, right? There's 1 volt technology, 1.8, 2.5, 3.3, maybe even some 5 volt ones around. So I set the threshold of where I want that to transition, but it's not the kind of thing where I'm setting a threshold per channel usually. A lot of times with logic analyzers, you set one threshold, and it's the threshold for the whole probe at least, right? So if you have a large logic analyzer that has 32-bit probes, and you have, say, 8 of them, that's a lot. Each probe of 32 signals has its own comparator or threshold value for all of those comparators. And then it latches it, right, from that external clock. There's an internal time base, but not interesting to us right now. All right. So asynchronous, I got to take a lot of samples, right? So this is the internal clock. Not interesting to us. This one's the interesting one. So here's how you set up the threshold, right? And this one has one threshold. It's set to this value, right? You got to pull that down. And these signals are set to that threshold. So there's 4 different possibilities of threshold on this given analyzer. Don't worry too much about this because ultimately we're going to use an internal logic analyzer, and it knows the threshold because it's the same as the signals that it's measuring. Okay. It is warm up here. So in a counter, right, you can see the least significant of the counter, 0, 1, 0, 1, 0, 1. The next 0, 0, 1, 1, 0, 0, 1, 1. Then 4 zeros, sorry, 4 ones, 4 zeros, and then presumably 8 zeros and 8 ones. So this is what that count would look like if I probed it on logic analyzer and I used a synchronous sampling. Why do I know it's synchronous? Because if I use an asynchronous sample, there'd be a little modulation here. This wouldn't be exactly the same size as this, and so on. So you can tell. If I have a bigger counter, and this is, I guess that's big enough counter, it will allow me to display that counter as an analog looking waveform. This is not an analog measurement. It's taking the digital waveform and displaying it as a linear signal. clock. If it was a synchronous clock, we'd see every we'd see a signal here, we'd see a signal here, and it would be FF and 0. But with the asynchronous clock, sampled very fast, right? Because there's, I look at this and I see that there's 20 or 30 samples between here and there. But now you see that staircase because the physical reality is that all of those signals don't change at the same time. And this is amplified by the fact that it's a poorly designed counter, but it's obviously for illustration for this picture. All right. So I have that picture here too. So in general, I have that still that linear sequence, but I get this thing right here, right? It doesn't look as even anymore. This is going from this point to this point, but this allows me to see all those points in between. The signal doesn't exist in the system. It's just a symbolic representation of the counter. Yeah, so if I have the counter doesn't click in the right sequence, I get this. But remember, if I have a synchronous system, we don't see this in the digital system either. So don't worry about the fact that these signals don't look quite right, because if we are sampling everything synchronously in the system, it's going to filter all this stuff out anyway. So this is just an example of the difference between a synchronous sampling and an asynchronous sampling. So, if this is a design class, I'd say the same thing, but I would say that you don't see these glitches because you are synchronously sampling it, unless, of course, your logic isn't fast enough, right? If you have timing failures, then it's a different story. Okay. So triggering. Triggering is the most important thing, most important advancement in logic analysis. So in a modern logic analyzer, I'll call it, it's more than just looking at a pattern. In fact, you can set up a state machine, and the state machine has conditional statements in it, and it has operations like if something happens at the beginning, then set a timer. Increment the timer at 1 and start this at the beginning. Go to next, goes to step 2. In step 2, it does a if-then statement. And the if-then statement does something. And I'm not going to dive into this. And here's the problem. This is really complicated. And I've used logic analyzers to find complicated problems. And when I did, it seems like every time I do it, it's separated enough that I've never used a logic analyzer that I happen to be using. So I have to learn this ugly, GUI-based state machine design product. And the next time it's a Tektronix logic analyzer, and wouldn't you know, it's different. And I have to learn how these menus and click buttons and everything work, but it's very advanced. You can do a lot of stuff here, and you can find something in the signal that's based on a set of events that leads up to the signal. I hope you're thinking right now, why don't you just use Verilog? And you'd be right. And that's the advantage of what I'm going to show you next, is that we don't have to deal with these things. We can simply write the code for what we want to see. Right. So here's, for example, here's the trigger event, and we've set the trigger to see that's a T right there. So we set the trigger to this point, and we set up a trigger that would sense the fact that the counter had stopped counting, right? Set a timeout, and that's how we get triggered here. Great. That's what this was looking for. And we're not going to use that method of triggering. I just wanted to show the point that you can do very advanced triggering in these tools. And you're going to want to do very advanced triggering when you do logic analysis. And here's zoomed in on that point where it stopped, and then finally the trigger. Trigger isn't shown here, but oh, it is right there. All right. So probing. This looks ugly, doesn't it? There's 1, 2, 3 probes. They're connected to these points. Remember, I said having a lot of clips was a problem, and you don't see a lot of clips here. You see these connectors. But what they did is they had the forethought on this board to put the part into some sort of socket that they could plug this interposer board onto, and then put the actual part here. And then they broke out the connections of that part into these connectors that were compatible with the logic analyzer. I've done this before, and there's a company called Emulation Technology, which I heard has been bought by another company. I don't know the name of the other company, but they build these things and they custom build them. And I've had my company spend thousands of dollars and built a board that wasn't as dense as it could be to come up with one of these fixtures so I could connect the logic analyzer to it. Now I don't think I've done this in 10 years, but I have done it, and I've needed to do it because if I wanted to put, let's say each one of these probes is 32 bits, so it's 32, 96. If I had to figure out a way to put 96 probes, little clips on this, it'd be impossible. One little disturbance of this thing and one of them pop off. And then which one was it? And what's the chance of me putting two in reverse or touching each other? All the things that could go wrong. So this is a nice solution, but it has some expense. It has the expense of the socket. It has the expense of designing the socket. It has the expense of building a board that has all this extra space on it. And connectors that are this dense have connection problems anyway, right? If you have 2,000 pins and you make the connector a bunch of times, you start to see intermittent connections in that. So remember I said all those problems with probing, and I amplified all the problems with probing. Now I'm going to remove probing completely. So we can add the connections, we can add interposes, or we can do integrated logic analysis. And that's finally the point, right? Almost an hour into this lecture, but with justifying how this is going to come together, we're going to focus on integrated logic analysis. It's a Xilinx term. Altera has the same thing. I know this class is a bit of ASIC and a bit of FPGA, but this actually has an application in both. All right, so a little bit of an aside. There was a time, and I have a story to finish this. So there was a time when if you wanted to do microprocessor design, you had to have a microprocessor on the board and an FPGA on the board. And the microprocessor was something that you pull out of the socket, you plug in something that looked like what I had on the previous page, and you plug the microprocessor on it. And then you'd have a cable that goes to a development system, which is where you wrote your code, and then you ran your code on it, and you could set breakpoints and blah, 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 blah. You could do all kinds of stuff. And it was very useful. In fact, it became the staple of processor design to do that. Processors got more and more complicated. And that connection became more and more difficult. Okay, let's talk about something else. So I started at Draper 14 years ago. Right around the time that I started at Draper, the group leader for embedded design got promoted. So it opened up a position for a group leader for embedded design. So figuring I'm new, I'm experienced, I want to be successful here, I applied to be the group leader. And when you apply to be the group leader, you have to give a presentation to senior staff and about your vision for the group. And my vision for the group was, if we're designing FPGAs and processors, we have to start designing FPGAs that have processors in them. Now, remember, this is 14 years ago, maybe 12 years ago. It wasn't immediately after I started. And I just felt that that was the future of embedded design, is having FPGA logic. And if you're familiar with Vivado and the Zinc board, you know I was exactly right. So I'm giving the presentation, and one of the senior staff, very experienced and intelligent analog designer, puts his hand up. Why would you want to do that? I had no answer. My answer was, because that's how it's going to be. That's how we're going to have to build these things if we're going to be competitive, if we're going to meet our size, weight, and power and cost goals. But how are you going to emulate the process, or how are you going to do the development? And I didn't have the best answer, but I knew the question was answerable. So right around that time, the microprocessor manufacturers were seeing the same thing. So what they started doing is putting a debug port on the processor. And the electronics of that thing that senses breakpoints, the thing that allows you to interrogate the processor and change it, they just put right in the processor. Because as the processors got bigger and bigger, that stuff stayed about the same size. So it became significantly less of a burden on the total size of the chip. So it was okay if they burdened every microprocessor with this debug logic, and then they just had a serial port on it. The test engineers always had a serial port that they used for self-test, and they called it the JTAG port. JTAG stands for Joint Test Access Group. And the JTAG port became the standard way of doing debug and test of the, but it also became the interface for this internal debug mode for the microprocessors. So wouldn't you know, at the same time, the FPGA manufacturers needed a way to get the FPGA program into the FPGA. They used JTAG too. So eventually, and maybe 5 years after this event, Xilinx came out with the Zinc processors. And actually before that, they had a different version. They had the Vertex 2 Pro with the processors on it, and you controlled both the FPGA and the processor through the JTAG port. All the problems are solved. Now, the good news is I didn't get the group leader job. And after experience of working at Draper over time, I realized that the worst job in the place was the group leader. So I actually ended up, I probably would have left, but I ended up on a nice, strong technical path, and it's been good and continues to be good. All right, so that's that. That's my story, but that's how we got here. And it comes also from ball grid arrays. Ball grid arrays, it's very difficult and expensive to socket them. All right, next. Here it is. Here's the JTAG connectivity. So I can take my PC and over what's usually a USB port, I go to this JTAG adapter. And these are anywhere from $5 on eBay to a couple $100 if they have more capability, right? And if you're doing, if you're using an FPGA, you use the manufacturer's device or a direct knockoff of the manufacturer's device. So that goes to a JTAG port. The JTAG port talks to your logic, it talks to your memory, and it talks to your CPU. Right? The tap controller is a test access port for internal tests. Don't worry about that. If we were talking about JTAG, we'd worry about that. But we're talking about how we can use it to load the configuration of the FPGA, load the software for the processor, debug the software, and tonight debug the hardware. Okay, that's what I've been trying to get to. Debug the hardware. So that's what we're going to do. Now, how do we debug the hardware? With logic analysis. And when we do logic analysis, we have to have good connectivity. And we're going to have good connectivity because we're debugging it from inside. So that gives us flexibility in connectivity, and it gives us full bandwidth. Full bandwidth meaning we don't have to worry about probe contacts, 1 meter cable, connection to an oscilloscope or logic analyzer, internal amplifier of said device, right? So we've solved all the problems that I've set up tonight with this JTAG connectivity and an integrated logic analyzer. So they call it ILA in Vivado, which is the Xilinx product. They call it ChipScope in the Intel product, right? It connects to their Quartus system. We're only going to talk about this because they are virtually the same. So this is a piece of logic that you get from the manufacturer that you compile into your FPGA, and it uses the otherwise unused block RAM in the FPGA. FPGAs have tons of memory in them, and rarely do you use all of it. So the extra, you use that for the logic analyzer. So that's good and it's bad. It's good in that you have to have extra memory. It's bad in that it does limit you. So remember, half an hour ago, I said we have to be economical about the amount of memory we use in this application because it is fairly limited. It's more limited than it would be in a standalone logic analyzer. Remember, this is virtually free. You already have the JTAG connection for the software. You already have it just to load the FPGA, and you're just using logic and memory that's in there. The software for this comes with the development tool. So it's not a $50,000 logic analyzer. It's free, but the $50,000 logic analyzer has more memory, and more memory gives you more depth of trace and more signals to trace. So we're going to be a little limited in both of those, but you don't need 512 connections, which you would get on that expensive logic analyzer. And then you look at it in Vivado, which is going to be another important selling point. Okay, so no connectivity problem. So here it is. This is the block. It's just a block diagram of the block, but it has a clock input because this is synchronous clock. It has a trigger in and a trigger out. So the reason for trigger in, trigger out, and then trigger out ACK and trigger in ACK is these can be cascaded. So you set the trigger up for one and it triggers all of them. Now you can trigger on a signal, you can trigger on a group of signals, or you can use this trigger in. This is where the power of HDLs come in. So if you need a very specific trigger, you need a trigger that does some state analysis before it triggers. So it looks at previous events, it sets timers, all the stuff that was in that awkward GUI menu, you can build logic here in VHDL or Verilog that's going to generate that trigger. So now using the tool that you already have, you can build very complicated triggers. I would hazard a guess that the triggers that you can build in a tool like this are way more advanced than the triggers that you could build in a conventional logic analyzer. And then it shows 1,024 probes. That's a lot. And you can cascade them. That's a lot too. But you know, you only have to connect the ones that you actually need. So you're not buying anything anyway. You have to be economical about that. But you can get a very good trace, and you can download this through the tool. One additional feature, all of these chips, both FPGAs and ASICs, use AXI, which is an extended AMBA bus, which is an internal bus used for ASICs. You can directly probe the AXI bus, which is kind of cool too. If you have more than one AXI bus, you can put more than one core in, cascade the triggers, and have separately analyzed AXI buses. So this is a really nice thing. And I've used this a lot. I haven't used a conventional logic analyzer in probably 10 years, but always put either this into a Xilinx FPGA or the ChipScope product into the Intel FPGAs. I know this is a class in FPGAs and ASIC, but I'm getting there too. All right, so here are the ports described, right? Nothing new. I think I described all these. So clock, the probes, trigger in, trigger out. You can read that. The trigger in and trigger out allow you to cascade them, but it also allows you to have a complicated trigger that's a HDL block that you wrote. Parameters, the important parameters are the depth and the number of probes. So you can have between 1 and 1,024 probes, and then the depth is in powers of 2. So 1,028 the depth up to 128K depth. I can tell you, if you're using 1,000 probes and 128K of depth, ain't gonna work. Right? You're gonna fill up all the memory. You're gonna run out of block RAM. I have had cases where I had a chip that used a lot of memory, and because it used a lot of memory, it had difficulty fitting the logic analysis in it. So what I did is I made changes to the chip for debug that would reduce the amount of memory that it used so I could fit more logic analysis in it. Did my debug, bring up all things I had to do, and then I went back to the full memory version of the chip and took the logic analyzer out. And other stuff here, which is less, how triggers work and things like that. But this is the thing. The number of probes, the size of the memory, and this probe width is just if you it's the number. You can group probes together, right? That's all. So anyway, that's that. This is all in a GUI. So you put the logic analyzer into your design, and then you open up a GUI on that block, and it allows you to set these parameters. Okay, so here it is. Here's the GUI. So probably everything that I just showed you is available here. I decided on 4 probes. And then the next page is going to allow me to decide how many bits each probe is. And then the number of comparators, I usually just use one. And then I'm going to trigger it on data and the trigger input. Right. Same stuff that I've talked about. I only have one in here. Then instantiate, so this is a little more information about that again. Okay. Now, the important part, really important part, remember those 500 or whatever I said, 96 probes, I think, in that example. Every one of those, I had to connect to a certain spot. If I wanted to change them around, I had to change them around, and I was limited to pins on the chip. Here, I effectively have the net list of the chip available to me, and I can pick any one of those signals to be probed, right? So this is a limited one, but you can actually look at the graphical view of the net list of the chip, and you can click on it. It puts a little bug. You click on the actual lines that you want to probe, and then you compile your chip. And when you turn on Logic Analyzer, it already has all those signal names there for you. I can't tell you how much this saves from a conventional Logic Analyzer. And it's right. It's connected to that signal. There's no intermittent connections. There's no bandwidth limitation. It just all works. And then if you need to change it, you just change this list, recompile, and go forward. Now, sometimes compiling the chip can take a long time, but you could also spend a long time trying to reconfigure tiny little probes that are popping off or touching each other or something while you're trying to do it. So this is very powerful. And what I find, you can also save this. So what I find is when I'm doing this in a really complicated way, I save this and I have a few different profiles. So depending on what I'm trying to do, if I'm specifically looking at the bus or if I'm looking at a specific peripheral, I put in the profile and I look at that, and then I change to a different profile. And then this is a little blurry, but then I go through the same dashboard that I use to load the software and load the hardware in the FPGA, and it brings up the Logic Analyzer dashboard, right? And it has the start, to wait for a trigger. It has single trigger. It has repetitive trigger, all the same things that a normal Logic Analyzer would have, and the scope had in my first example. There's not a lot left here, so I'm just going to keep going. Instead of taking a break. It's all recorded anyway. And then we'll be done. We'll probably be done about 8 o'clock. So let's just go instead of stopping, taking a break. There's no homework to discuss tonight because homework I already went over it. The homework is due next week. All right, so you do that and you trigger it. Trigger immediate means just show me the signals, and then trigger, this trigger right here, triggers based on the trigger that you've set up. And boy, this looks a lot like a Logic Analyzer, right? Good thing. And here's the thing. So this is the whole trace, and then you can zoom in on a piece and you see something like that. Also, in these tools, they have simulators, or you can open third-party simulators from them. So what you can do, this is the point of the whole lecture right here. What you can do is compare what's going on in your chip to your simulation, or you can use this as a simulation accelerator. And that's where the connection between FPGAs and ASICs come in. So if you're trying to simulate a very specific part of your ASIC, you can load it into an FPGA, just compile it into an FPGA, use this tool to give you observability of the part, and you can do your simulations effectively in real time, as opposed to waiting for a long sequence of events to happen in simulation. So there you go, right? I've built you in an hour and 10 minutes now a simulation accelerator out of an FPGA reference board. Now, this is a common practice, and it's an important part of verification these days. You can't do everything this way. You can't observe everything. And your stimulus is something that we'll talk about in a minute, but the stimulus is also a little limited. So what does that mean? Well, when you wrote stimulus for the project or whatever, you called bus functional models. And I've been saying that those bus functional models don't have to be synthesizable, but they probably can be synthesized. So when you did take this unit and put it into the FPGA, you could also compile pieces of your stimulus generator, put those in the FPGA too, and you could even put response checkers in there and use this tool for observability. Right? It's like magic. So now instead of spending $1 million on a simulation accelerator, which you could easily spend $1 million on a simulation accelerator, you can buy a few $1,000 FPGA development board. I'm sorry, I'm looking where the camera used to be. You buy a few $1,000 FPGA development board and you have that capability. Now, the FPGA might not be as fast as your ASIC. You probably will have to slow your clock rate down, but it scales. If your simulation requires external components, that might be hard unless you can get that information from some other component into the FPGA. But what this is first of all, something that allows you to correlate actual behavior to expected behavior by running the simulation and then running the logic analyzer on the part and comparing them. And you can dump files out of both the simulator and this and just do a post-processing on it. Done it 1,000 times. I don't know about 1,000, but I've done it a lot. This is an extremely powerful verification tool, finally, right? We talked a lot about debug, but don't hesitate to use this method for verification. So setting up the trigger, you can use their awkward method of setting the trigger, or you can write code and make the output of that code the input to the trigger or connected to the trigger input of the internal logic analyzer. And now you can set up very complicated triggers. They don't even have to be complicated. They're application specific, right? They're doing exactly what you want them to do. Auto trigger just triggers everything. If you notice here, it's a little hard to see, but this is the hardware manager, and there's the logic analyzer. This thing right here is the part. So when you send the program in, it comes up and says programmed here. So I don't have a processor here, but I do have the programmable FPGA and the logic analyzer. This XADC is a thing that allows you to measure the voltages on the chip. We can do glitch capture. I haven't talked about glitch, but a glitch is a signal that changes and changes back within one sample. So glitch analysis is something that those expensive logic analyzers give you. This has limited capability to find glitches. And it does increase the amount of memory that you use, because remember, now it has to look at before and after the signal. All right, that's that. That's internal logic analysis, and it's very valuable. Let's extend it a little bit. This VIO block is a low-speed connection, and what it does is it goes in that hardware manager, and it lets you write a limited number of values, and it shows a large number here, but let's say that it's a small number. So let's say you could get 10 output signals, and I only want to talk about output. So this is 10 signals that go to your chip, and they're set and cleared by the JTAG port. So you have another item in your hardware manager that allows you to set values. So why? There's a lot of things you can do that aren't interesting to us right now. What is interesting to us? Well, remember I said sometimes I have profiles of probes. I have a set of probes that I use for a given communication interface. I might have a set of signals on the bus. And I said that if I want to have one, I compile that in. Well, what if I don't want to compile every time I want to change the signals I'm looking at? What I could do is take the groups of signals and multiplex them. And the input to the multiplexer is the output of the VIO module. Isn't that cool? So now I can write a value, and not a lot. Let's say it's 4. So I write a value 0, 1, 2, or 3, and it selects a multiplexer that puts the proper set of inputs into my internal logic analyzer. Or I might also have some modes of my triggering, and I decide what mode of triggering I want based on how I set these outputs. So this is not fast. right? This is kind of human speed. But the advantage it gives you in increasing the potential for the probes that you're going to look at in the logic analyzer is very valuable. Input does the same thing, gives you the static value of inputs. I have to say I've never used the input part of this. Can't think of a good use for it, especially for this application, but I've done exactly that. I've had like 8 profiles of signals that I wanted to put into the logic analyzer. I set them up separately, put it into an 8-to-1 multiplexer, and then took 3 pins out of the virtual output and connected it to that multiplexer, and then I could pick the profile. Again, worked really nicely. So you configure it similar to the way you configure the other one, how many probes and how many pins per probe and things like that. I've never done a significant number, like 3, 4, 5 kind of signals. Same with inputs and outputs, right? So you configure the number of inputs, number of outputs. It's slow because you have to change. It's a little window on the hardware manager, and you type a new value in the window and just click off the window, and then it changes the value. I think that the one time I did use the inputs is I didn't trust this thing. So all the outputs I connected to the input too. So I saw that when I changed the output, that input value changed. But it is literally human time, right? There's no like time base on this thing. You click it, it goes down the JTAG port, changes the value. But that's not the point. Isn't speed. The point is configurability. And there it is on the dashboard, right? So there's the values. I'm sorry, this is the one. So there you go. These pictures are a little blurry. This user guide, which I can't read on the screen, is all this is outlined in the user guide. There's a lot of other stuff you could do with this stuff, but I'm limiting the discussion to what adds value to verification, and that is how you would set up simulation in hardware. Now, if you're building giant ASIC, the whole ASIC is not going to go in the FPGA. But if you're building giant ASIC and it has one computational element in it that you're trying to simulate, then you put that one computational element into the FPGA, and now you can you talk about exhaustive simulation. If I had a 32-bit multiplier in simulation, it's going to take a certain amount of time, right? Because simulation clock cycles go pretty slow. If I could put it in here and run it at, say, half the speed of the ASIC, I could get a lot more vectors. I could also build, for my stimulus, I could put pseudo-random number generators in that would give me that. So I was successful with this once, and that caused me to want to do this. I had somebody who designed an error detection and correction algorithm. And this was an important algorithm for the ASIC. It was brand new, but it was a selling point of the ASIC. This is a chapter in my book for this one case study. So there was no way we could simulate it. The math was just too deep, and we could simulate like a few cases. But when you come up with some new kind of algorithm like this, what you do is you effectively have a value and you walk an error through it. So if you have a 32-bit value, you flip the first bit, the second bit, get the idea, right? And then you go to the next value and you walk it through and walk it through. And this is a difficult process, and it's impossible in simulation because it's too slow. So what you do, keep talking to that microphone. What you do is you put it into an FPGA, right? We build it in ASIC, but we put it into an FPGA. We built that algorithm that walked the error through. We had the actual results and the expected results, and we compared them. So we were putting the response checker in this, and we figured out what the clock was. And of course, it was too slow, but it didn't fill the FPGA. So we put like 10 copies of the circuit in, and we indexed them so they were all looking at a different space in the algorithm. And we turned this thing on and went home for the weekend, literally went home for the weekend, came in on Monday, and it had failed. And you think, oh, it failed because it got too hot in the room or something like that. No, it found an error in the algorithm. And this would have been embarrassing, right? This would have been an error on a technology that we were basing our marketing on. So found the error, fixed the error, ran it. It took like a week to do that, ran it the next weekend, and sure enough, it all worked. And we had significantly more confidence in it. And we actually changed the marketing to say that, hey, this is exhaustively tested, as opposed to potentially we would have sent out a product that had a bug in it. Okay. I just put these couple of slides in for information. There are bit error rate testers in FPGAs as well. So this is an embedded test equipment in the FPGA that does bit error testing, and they specifically do it for those high-speed interfaces that are available on FPGAs. So not important for us, but one thing to note here is it's also generated and detected by the boundary scan, the JTAG port for boundary scan. You configure it similar to how you configure the other stuff, protocol and things like that. Set up the clock. If you're actually designing high-speed interface, all this stuff would matter. And you get a nice pretty picture, which is the eye diagram, right? So as the signals transition from low to high and high to low, like let me draw up, over, down, and over, down, over, and up, right? So this is the, this is the area where the signal is in transition, right? During this area right here, you have the highest probability of detection, right? So if you're sampling right in the center of this area, you're going to sample true data. As you move to the edges of this, you're likely to sample in a transition and get wrong data. This isn't a class in bit error rate testing or communications, but that's what this does. So suffice it to say that there is other internal test equipment on the FPGA. All right, that's that. Was this interesting? It was interesting for me. I enjoyed putting this together because it was something that I've done that really had a result that changed my ability to exhaustively test things. And you know, we'd use this for other things, but that specific case, and this had to be 15 years ago because it was before I was at Draper. It allowed us to exhaustively test a brand new algorithm. And more importantly, it found a bug in it, which the customers would have eventually found the bug for us, but then it was an ASIC. So we would have had to respin the ASIC. And as a startup, that was prohibitive. And this was maybe $1,000 FPGA board. It wasn't like these really high-end $10,000, $15,000, $20,000 boards. But by the fact that we could put the algorithm in it and put like 10 copies of it in tens of hours, it finished and it tested every possibility. And when it was done, right? We knew the algorithm was good. All right, questions? I suggest, so if you haven't taken my FPGA design class and you enjoyed this class, you should take the FPGA design class. They're not like prerequisites of each other, but they're both two pieces of knowledge that go together. If you do take the FPGA class, I suggest that you buy even the cheapest. You can get an FPGA development board for like $80, various ones. That's kind of the low end price point. Go through the software and do this, right? Even just throw an adder in there, but build stimulus, design a response checker, and run the algorithm through it. And see how fast it goes, and run the same thing in simulation, right? The same stimulus, same response checking, do that in simulation. And just learn this technique because it will be valuable to you if you're either a verification engineer or a design engineer. And just the final plug, the FPGA class is running this summer. So you can take it in 6 weeks and be done with it. I tend to be a little easier on homework. Not that my homework isn't easy to start with, but in the summer where it happens so fast, there's no real technical component to the homework. All right, that's that. That's the secret on the FPGA class. If you've already taken it, tell all your friends if you liked it. If you didn't like it, tell me what you didn't like about it. All right. I don't have anything else unless you have questions. The codes, is that what the question is? I didn't see that come up, but I'll assume that someone's asking me for the code. The codes are 201A is 7004 and 201B is 0571. So again, 201A 7004 and 201B is 0571. Questions? Ask for the codes. I think. Did someone ask a question that I didn't get? I heard the beep happen, but I don't see any new. Last chance for questions. My dog slept through the whole thing. She's barking her head off. I'm alone in the house tonight, and I was afraid that she would be barking. And up to like 6:28, she was still barking, and I was feeding her treats. And I must have filled her up because as soon as I started talking, she fell asleep. Hopefully, you're not thinking me too. Anyway, one last chance for questions. See people leaving. Thank you for showing up on such a nice night. Beautiful weather. Enjoy the weather tomorrow too, because it's not going to stay that way. But have a good night and thank you. And remember, homework 8 is due next week. All right. Have a good night. Bye.
Thank you, Professor.
Thank you.